Hey everyone, and welcome. So today we are diving headfirst into one of the most mind-bending and exciting frontiers in all of technology. We're talking about the convergence of artificial intelligence and quantum computing. I mean, think about it. Two of the absolute biggest revolutions in computation. And we're going to explore what happens when they finally team up.
So let's just cut right to the chase. What really happens when these two monumental forces meet? And, this isn't some far-off sci-fi idea. This collision is actually starting to happen right now, and it's already beginning to completely reshape what we thought was possible in science and tech.
All right, so let's break this down real quick. On one side, you've got AI. We know it. We see it everywhere. It's incredible. It's sifting through mountains of data, finding patterns, and making smart predictions. But on the other side, you have quantum computing, which is, well, it's a completely different beast. It plays by the bizarre rules of quantum mechanics, using phenomena like superposition, where a single qubit can be a 0 and a 1 at the exact same time. It's wild, I know. But this allows it to explore a vast number of possibilities all at once, solving problems that are literally impossible for even our best supercomputers.
And that right there brings us to this incredible new field, quantum AI or QAI. What's so fascinating is that this synergy, this team-up, isn't just a future promise. It's happening today. Even with large-scale quantum computers still being a work in progress, AI-driven techniques are already having a massive impact on quantum research, right now.
And look, this isn't just hype. The experts who live and breathe this stuff are all saying the same thing. This convergence has the potential to be utterly transformative. It's this amazing two-way street where each technology strengthens the other, creating this powerful feedback loop that just accelerates innovation.
Okay, so let's head down one side of that street first. How quantum computing is basically set to give AI a massive power-up. This is where the future of AI gets really interesting.
I love this analogy. It's the perfect way to picture it. You see, quantum isn't trying to replace the powerful AI engine we've already built. No, instead, it's like we're bolting on this incredible supercharger, making that AI engine faster, way more efficient, and suddenly capable of tackling whole new kinds of problems it couldn't even dream of touching before. So, what does that actually look like in the real world? Well, it's what we call a hybrid approach. You take a really complex problem and you find the gnarliest, most computationally difficult part of it, like finding some deeply hidden pattern in a huge data set, and you hand that really tough piece over to the quantum processor. The quantum computer does its thing, finds that hidden gem, and then it passes that insight back to a regular, classical AI to make sense of it all and give us the final, useful answer.
And the payoff here? It's huge. We're not talking about small improvements. We're talking about radically slashing the time it takes to train machine learning models. It could mean we need way less data to build a really powerful AI. And maybe most importantly, it could let us uncover complex relationships in data, say for developing new medicines, that are just completely invisible to our current computers.
All right, now let's flip the script and walk to the other side of the street. Because this is absolutely not a one-way relationship. It turns out, building and running these quantum computers is so ridiculously hard that we actually need AI just to make them work at all. And this is such a great way to think about it. These quantum machines are unbelievably fragile. They're sensitive to the tiniest little vibration or temperature change. They're just so finicky and complex that a human trying to fine-tune them is, well, it's pretty much impossible. They need an intelligent architect running the show, and that architect is increasingly becoming AI.
The role AI plays here is, well, it's everything. AI helps us design the actual physical hardware. It figures out the most efficient way to run our algorithms on that hardware. It even helps us understand the noisy, messy data that comes out of these machines. But maybe, just maybe, its most important job of all is tackling errors. Think of quantum error correction, or QEC, like this. It's the most brilliant, fastest spell checker you can possibly imagine, but for quantum bits. Qubits are super prone to making mistakes or decohering. An AI can actually learn the unique error patterns of a specific quantum chip and correct for them in real time. This is a total game changer, and it's what makes the whole calculation something you can actually trust.
So when you put all these pieces together, you start to see the big picture. The future isn't a battle of quantum versus classical, no way. The future is hybrid. It's a seamless, powerful integration of both of these worlds. But it's a future that still has some really big hurdles we need to clear first.
Okay, but let's be real for a second. We're not there yet, not even close. We're still struggling with the sheer number of qubits we have, and more importantly, their quality.
There are also really tough fundamental problems, like just figuring out the best way to load our normal, classical data into a quantum state. And then there's this weird problem called barren plateaus, which is basically like the model hits a dead end in its training and just stops learning. It's a huge challenge.
But the good news is, there's a plan. There's a roadmap to get us there. In the next few years, the focus is on finding those first real-world quantum advantages, probably in areas like chemistry. Then, in the midterm, it's all about scaling up these hybrid systems and getting much better at error correction. And the long game? That's the dream. Truly integrated systems where the AI and the quantum hardware are designed together from the very beginning.
And this is why all that hard work matters. The real-world applications here are just staggering. Imagine discovering life-saving drugs in a fraction of the time by perfectly simulating molecules, or making self-driving cars safer and more reliable. This isn't just about making faster computers for the sake of it. This is about solving problems that affect all of us.
And that brings us full circle, right back to where we started, with a really big question. As these two revolutionary technologies continue to merge and empower each other, you have to wonder, could this incredible partnership be the key that finally unlocks the solutions to some of humanity's biggest, oldest, most fundamental challenges? We don't have the answer yet, but for the first time, we can start to see a path. Only time will tell. Thanks so much for joining me.